We're talking about the wave structure of matter. For 3,000 years, everybody has thought that matter had to be little bits of sand, little particles, just like the Greeks thought. I think most scientists, they made sandcastles on the beach. When you make a sandcastle, you begin to think, well, this is the substance of which matter really is. So it's pretty hard for them to get rid of these ideas. But the truth of the matter is, all the experiments, the observations that scientists make agrees that there has to be a wave structure of matter, and only wave structure. And only wave structure.
What's wrong with the particles?
They just don't fit.
Why?
They don't match up with the observation. There's a thing called a wave-particle duality, and it's a big puzzle. Sometimes a particle looks like a wave, or at least what people think is a particle. They all tend to look like waves if they get small enough, because they are waves. The photon, for example, energy goes from here over to here. Nobody sees it move, so they make up a particle called a photon. Never identified, and it violates all the laws of electricity and magnetism, of which it is supposed to be made, but it isn't. So this is a great puzzle created by particle notions. Nobody explains it. It just happens. This is the religion of science. Nature is like the church. If you don't understand something, you just say it happens. Nature did it that way. And you stop thinking, stop looking for answers. The mathematical physicists are perhaps the most deceptive of the lot, because they tend to pull the wool over everybody's eyes. They got all the A's in the algebra and calculus classes, and all the rest of the scientists are kind of afraid of them. So they get to make more speculation than anybody else. What people think are particles are spherical wave structures consisting of an outgoing wave combined with an in wave. Mathematicians are fairly happy with this, because these are the only two possible solutions of the equations. So that part is okay. Now the center of this structure behaves just like a particle. The only problem is not many people know it yet, because not many people have investigated it. As far as I know, the only people is a guy in Australia named Jeff Hazelhurst and myself. And there's a few other people now are beginning to see it, and they're looking into it. Space. Space is the medium of these waves. Space is the thing we still know least about. Space and its character and its structure is the research forefront of the future. Just because we can't see it, because we can't put our hand on it, we conclude it's really nothing. We have a phrase, empty space. All the logic of astronomy and physics tells you that it is not empty. It is the medium for the waves that go from you to me. 10 to the minus 12. That is 1/millionth of a million meters.
How many wave centers make up the construction of your body?
Oh my gosh.
Roughly.
Roughly. About 10 to the 25. That is a 1 followed by 25 zeros.
How do you explain, in the space going out into our universe, where these in waves come from and where do the out waves go to?
Well, at first sight, if you just consider one wave center, and you imagine it got out waves and it got in waves, you're immediately puzzled, because you say, well, gee, the out waves go on and on and on, and they get lost out there in infinity somewhere. And the in waves, you immediately say, where did they come from? But a serious mistake was to think of it all alone. You must realize that the our universe is just filled with wave centers. Every hydrogen atom, this pencil, wave centers everywhere. And so wave centers, the waves go out and they interact with other wave centers. So there's a lot of exchange going on.
Our outwaves become their in waves because a wave is a wave. It has no tag on it saying, hello, I'm an in wave or I'm an out wave. It's just waves rippling through space.
In waves, mathematically at least, have a somewhat different character than an out wave.
Mm-hmm.
So you simply can't switch them around.
Yes, that's only relative to one particular wave centre though. Once
Right.
they're flowing back out,
Right.
and they can become part of the in wave of another wave centre somewhere else.
Right, right. There's also another factor, which is still mysterious, in that these waves are exponentials rather than sine waves. The solutions to the equations are e to the I omega t, which is the same as cosine omega t plus I sine omega t. That is the imaginary number, square root of -1. And it's not quite clear what this does to it, or how it changes the character of the wave.
Well, it seems to me, if you're saying that these particles are in fact spherical standing waves with a particle effect at their wave centre, that's a very obvious explanation of the particle-wave duality. Why isn't it obvious to everyone, and it hasn't been obvious for the last 100 years, that this is an obvious solution to describing matter in space?
I think people are just creatures of habit. People get in a habit. It's hard to change.
They just had a habit of thinking of particles. and as
Exactly.
particles. What did Einstein think matter was in his general relativity?
Einstein, one of the most misunderstood people in the world.
Yeah.
Everybody imagines Einstein as declaring there are 4 dimensions and time goes backwards and frontwards and nothing is the way you really see it. But no, he thought carefully and logically and almost came to all the right conclusions about particles. He said they have to be expended. He realized that they have to interact with each other. You can't just say, it happens. Nature made it that way. No, he realized that they have to be spherical, have the symmetry, because there's no other symmetry that's possible. We live in a 3D universe.
So what did he imagine instead of the particle? What did he think matter was?
Unfortunately, he lived in the aftermath of a famous man called Maxwell. Maxwell was the man who wrote down equations for radio waves before there were radio waves. And lo and behold, another guy named Hertz came along and discovered radio waves. And everybody said, gee, that's great. Maxwell must be right.
And what did Maxwell use? What was he assuming existed to discover?
He assumed there are
these
electric
waves?
fields and magnetic fields, and these fields somehow go out from particles. And they exist there, out around every particle, sort of like a halo of light. And when another particle gets into the field of another particle, they interact. One, they pull together or pull apart. And but the only problem is that these fields don't respond to experiments that way. Apparently there are no electric and magnetic fields. They're just a mathematical help. Very useful. They give you the right engineering answers, but the fields aren't real.
Einstein assumed that matter was a spatially extended field, spherical.
Right.
So what's the difference between Einstein's view and your view of matter? And what are the similarities?
Research in energy transfer, and which is what we're talking about when we're talking about forces between particles. Research in energy transfer has shown that it is always quantum mechanics which gives the correct description. That is, one particle changes a quantum wave state, and for example, that might be a source, and somewhere else, another particle changes its state exactly the opposite way. This one goes down a certain amount of energy, and this one will go up a certain amount of energy. Exactly, that's the conservation of energy. We realize that all energy is transferred in this way.
It's one of the very important measurements to show that how the W coupled to its particles to produce a finite interaction.
Forces between particles. Research in energy transfer has shown that it is always quantum mechanics which gives the correct description. That is, one particle changes a quantum wave state, for example, that might be a source, and somewhere else, another particle changes its state exactly the opposite way. Another particle changes its state exactly the opposite way. This one goes down a certain amount of energy, and this one will go up a certain amount of energy. Exactly, that's the conservation of energy. We realize that all energy is transferred in this way.
Vessel for 3 quarks, and they're so tightly bound that if you try to pull it apart, the little pieces of gluons that hold it together break apart, and they produce more particles and more particles and more particles, but you never get free quarks. But anyway, the thought is that initially in these experiments there would be another size, another thing. The quarks would actually be composite particles, and they would in turn be made out of subquarks. And there was a lot of theory, at least among some people, and a lot of excitement that maybe you could discover subquarks in these experiments. Well, E plus E minus annihilation at the z-pole actually was a whole set of very nice experiments. They were very precise experiments, and they verified the standard model. They were able, because of the high statistics and the good detectors and the cleanliness of electron-positron scattering, they were able to measure many of the parameters of the standard model. For example, how a bottom quark couples to a Z boson, how a charm quark couples, etc. That the electron-positron measurements produce the most precise value of the Weinberg angle. They produce the most precise value of the Z boson mass, and they continued at the electron-positron collider at CERN above the Z-pole, and they were actually with sufficient energy to make charged W pairs. So they were able to make a W plus, which is the mediator of the charge current interaction, with its companion antiparticle, the W minus. And by measuring the threshold behavior, the energy behavior of how strongly the electron and positron annihilate to produce this W pair. They could actually measure the curve, and that curve was one of the very important measurements to show that how the W coupled to its particles to produce a finite interaction.
Smallest space.
A single particle all by itself doesn't do very much. But if you take two particles, a proton and an electron, and you put them together, their waves join. And their waves join with certain rules. Electron waves will form patterns. The violinist knows that there's patterns inside that violin case. So a single particle all by itself doesn't do very much. But if you take two particles, a proton and an electron, and you put them together, their waves join, and their waves join with certain rules. Electron waves will form patterns. The violinist knows that there's patterns inside that violin case. So in the same way, these patterns form between particles. Helium is more complex than hydrogen, or you combine a hydrogen with an oxygen, then you get very, very, very complex arrangements. And of course, every chemist and a biologist knows these arrangements as the atomic table. Any exchange in one of these complex wave structures can only happen if it goes to one wave structure to another wave structure. It can't go halfway between, because the wave structures have to be like waves on a string. You have a violin string, you pluck it, always has the same note. That is, the waves on it are a pattern.
Certain frequency of a standing wave.
Yeah, it's just what they call a standing wave. Kids wave a jump rope up and down. It has always a fixed pattern. Well, the wave patterns of atoms and molecules have fixed patterns. When energy changes, it changes moving from one pattern to another pattern.
And only certain are allowed, and that explains why
And only certain
energy states are allowed. Okay.
People ask me, why did you become a physicist? The fact of the matter is, I never wanted to become a physicist. I wanted to be a fix-up man. When I was a kid, I always fixed things. The neighbors had little pieces of machinery, electric irons, toasters. They would bring them to me, and I would fix them, and I charged them a nickel each. And I got to like this. So as I grew up, I wanted to know how everything works. I went through high school, read every copy of Popular Science and Popular Mechanics series in the library. I even had them go out and get the old stacks for me. I wanted to know how everything works. Naturally, I studied engineering. I didn't really want to be an engineer. I didn't want to build dams. I didn't want to work in a chem lab. I just wanted to know how to fix things. I realized that industry was making machines a lot faster than I could learn them. And it was hopeless. I could never learn how to fix everything. I decided I would just narrow my horizon, my goals. I would just study the basic things of science, and that's physics. I went to the University of Pennsylvania. I got my PhD in nuclear physics.
What year?
1958. And I went to Indonesia. That sounded like a great adventure. I thought I was going to live in a bamboo house on stilts so that the tigers couldn't get in, you know. Well, there hasn't been a tiger in Indonesia for at least 100 years. I was a professor of physics and a professor of electrical engineering. Let's see, after Indonesia, I came back to Massachusetts, worked for the Apollo project. at MIT. Our goal was
Cool.
to navigate the spacecraft onto the surface of the moon. And that was an interesting job. I tried to solve the problems of what the moon is made of, the surface. Everybody worried that it was a big 30-foot deep layer of dust. And if it tried to land on it, it would sink out of sight. So, in fact, nobody dared land it in the flat regions. They all decided they had to go in the hills, the rocks, for fear of the dust. Eventually, we worked out that the dust was a thin layer.
How'd you work that out?
Well, you calculate how much dust is being made, how many meteors are striking the moon every year, and pretty soon you realize that there isn't too much dust around. You could also calculate how fast the dust gets driven off into space. But nobody really trusted that sort of thing when you got a spacecraft, which costs $10 billion. I guess the Aerospace Corporation in Los Angeles, we were launching satellites mainly to circle the Earth. There was a lot of space left over on these satellites. Scientific experiments were done. We also had the GPS, Global Positioning System satellites, created by the Army and the Navy. Yeah, you can find your way around within about a foot anywhere on the Earth.
Which sort of tells you that these things are all interconnected through space, doesn't it?
Oh, yeah.
They can all interact with each other.
As a matter of fact, when I was there at Aerospace, I started to write a paper using electromagnetic waves to sort of make a grid work throughout the whole solar system.
So you were using electromagnetic waves as a mathematical tool before you discovered that they were only mathematical approximations to spherical standing waves in space. Is that correct?
Yeah, I didn't really start to think about the structure of matter until 1985.
You'd retired by then?
I never retired. I had some research grants from NASA. I was working on polarization of light off of asteroids and the moon. That was a fascinating thing. No one knew why light reflects off a powdery dust surface like the moon or an asteroid or Mars or Venus. Measurements had been made for some 80 years. I started working on this problem when computers started to get powerful around the 1960s. So I set up a computer program to calculate how a ray of light would come in, bounce around, come out again. And with a computer, you could bring in a million such rays, and one by one, you find out how they come out. My program took an hour to calculate this. Today, people are doing it, and it doesn't take 10 seconds to do it. The computers have gotten so powerful. But anyway, it was very simple, actually. This problem was simply because rays come in, they hit once, hit a second time, and come out. So this double reflections produced the experimental data. This made me very, very happy.
You were the first person to discover this.
I was the first person to discover it. And it happened one night at about 3 in the morning. My eyes are like this, and I'm pushing a few buttons, and I looked at this plotter. Oh, my God. Look, 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 look. It's exactly the way experiments are. And I was so excited, you know.
Okay, so how did you discover the spherical standing wave structure?
I was curious. 1955, I took a course in quantum mechanics. And this was a graduate course. And I had never had a course, any course in quantum mechanics. I assumed I was very stupid. I never understood the origin of de Broglie waves, which says that a particle goes along like this. It has a wave which is inversely proportional to its momentum. Planck's constant divided by the mass times the velocity. That's called the de Broglie wavelength because de Broglie first proposed it. And of course, de Broglie didn't know where it came from either. Nobody ever knew. But I didn't know that they didn't know.
So you thought you were
I just thought I was stupid. I never opened my mouth in a class. 30 years later, I just kept thinking about that thing, and it just bothered me all the time. One day I was reading a book called All About Waves by a professor at Harvard. It suddenly occurred to me that there must be some kind of a complicated Doppler going on. I wrote down a few equations. I discovered that only if you have a combination of an inward wave and an outward wave do you get the de Broglie wavelengths.
You're talking about a combination of an inward wave and an outward wave of two different particles.
Yeah, two different particles.
So you're talking about an interaction of four waves.
Right. There's a particle here, a particle there.
One's moving relative to the other.
So there is relative motion. Therefore, if you write these equations out, you get that the de Broglie wavelength is there. And I was also amazed to discover that Einstein's increase of mass was there. All the things which happen with relative velocity showed up. And I said to myself, this is so simple. I didn't think I discovered anything.
I must admit, when you tell me this, Marlo, it sort of gives a shiver down my spine.
Oh, yeah?
Because what you're telling me is that you've united quantum theory with Einstein's special relativity.
Yeah.
In that one equation.
Yeah, I did.
That's what you're telling me, isn't it?
But this seems so simple to me because these simple bits of algebra weren't all that complicated. So I says, yeah, this is a natural result. I'm sure somebody else has already found this because people investigated quantum theory and waves, and people have been using in and out waves for 30 years. They always thought they were imaginary, though, not real. I went back and I searched for 6 months, and little by little I realized nobody had ever found this. I must be the only one. But it took several months for me to realize that. When I realized it, I said, gee, I really got something. So I kept on studying and investigating it. And, of course, the result is this book. Just tells all of that work.
So what's the difference between Einstein's view and your view of matter? And what are the similarities?
Research in energy transfer, and which is what we're talking about when we're talking about forces between particles. Research in energy transfer has shown that it is always quantum mechanics which gives the correct description. That is, one particle changes a quantum wave state, and for example, that might be a source, and somewhere else, another particle changes its state exactly the opposite way. This one goes down a certain amount of energy, and this one will go up a certain amount of energy. Exactly. That's the conservation of energy. We realize that all energy is transferred in this way. Therefore, the only conclusion is that the electric fields are descriptions of large numbers of the quantum transfers.
That's so a blending of lots of little energy jumps gives rise to what appears on a large scale as a very smooth, continuous energy exchange. But when we started looking closely enough at one electron in a molecule losing energy to another electron somewhere else, we found that it was in bits.
Someone
this is what Max Planck did in 1900, didn't he?
Planck discovered this.